this series, which has terms that are in absolute value, at least, they're 1 over k squared. So, but there's minus signs kind of interspersed in no definite pattern here. And what you did in parts A and B was to think about why it is that the sum of the series that's written has to be less than the sum if all of the terms were positive but had the same size, and why that same series has to be bigger than the series that you would get if you had negative signs on all of the terms. So in the end, what we've then shown is that our series is sandwiched in between those two sums. So I'm going to go ahead and give this series a name. So I'm going to go ahead and call our series the sum of BKs, and BK will be is either plus or minus. Actually, the way I think I will say this is that the or the absolute value of BK is equal to 1 over k squared, but I haven't really specified what the sign of BK is. So what we know is that the sum of BK has to be between the sum of 1 over k squared and the sum of minus 1 over k squared. And these numbers, these series have actual limits. So let me just call whatever the sum of 1 over k squared is, let's call it L. Then if I negate every term, then that sum on the other side will be minus L. So what we know is that our series must converge to something between L and minus L. And the rationale is similar to when we were thinking about the alternating series test, but it's not quite as clear cut because we're not always jumping back and forth over the limit of the series, but certainly these terms are decreasing to 0 very, very quickly. So the terms BK are shrinking in size very, very quickly. And in fact, if we added them all up, they would sum up to some finite number. And so if we subtract a few of them, then we're still approaching some finite number. So that's a little bit of a hand-wavy way to think about what's going on. Here is that, if we added them all up or if we subtracted them all, we would still get to some finite number. So if we're doing a mix of those, we should still be approaching some finite number with the partial sums. So all of that is to say the following result. So we'll need a little definition here. If we start with any series, and there we're just not specifying the sign of the individual terms. If we start with any series, if the related series, so I'm actually going to talk about the second of these definitions first. If the series that you get by taking absolute values around every term of your series, if that series converges, then we say that our series converges absolutely. And the key fact that we just sort of described in your previous activity is that if a series converges absolutely, then it must also converge. Of course, the limits don't have to be the same thing. So, and in fact, they won't. If AK has some minus signs, some negative terms in it. So that's what we saw in the last activity. It may still be the case, though, that a series may not converge absolutely, but it may still converge. And in that case, that's what we call here converging conditionally. And so in particular, there are series, and we in fact saw one. So, okay, here we'll just think about the alternating harmonic series. We saw that series converges conditionally, but if we looked at the absolute values, the series does not converge absolutely because the series where you take the absolute values of all the terms is just the harmonic series, which diverges. I had one other note here, which is that absolute convergence allows us to use all the tests for convergence of series with positive terms. And that's because if in general, if you have a series and you recognize that it converges absolutely, then you can automatically conclude that the series converges. So this series here, with terms that are in absolute value 1 over k squared, but the signs are randomly thrown in there, we automatically know this series converges because we know that 1 over k squared, the sum of that, converges. And so the idea then is that if you can recognize that replacing your series with this related series of just the positive, just the absolute values of the terms, if you can recognize that converges, you automatically know that your series with arbitrary signs thrown in will converge. And so in particular, right, given an arbitrary series, sum of AK, you can use the tests for positive series. So comparison, limit comparison, etc. Use the test for positive series to check the convergence of the sum of the absolute values of AK. And then if you have convergence, then you can conclude that your series converges. Now, if you do not have convergence absolutely, then you cannot conclude that your series diverges. Then you have to investigate further. And in many cases, what will happen is you'll check the alternating series test if you actually have an alternating series. If you don't have an alternating series and your series does not converge absolutely, I think I would start thinking about partial sums, the sequence of partial sums, and start looking at whether that converges or not. Okay, so at this point, I would like to conclude by giving you an opportunity to try a few of these. So go ahead and determine whether each of these series converges absolutely. If it does not converge absolutely, investigate whether it converges conditionally. And so this will be an opportunity to kind of go back and review previous tests as well. So what I will do is on your copy of the handout, I'll go ahead and add the answers to the bottom after assignment H. But I'd like for you to go through and show your calculations and what tests you're using and what evidence you're using for your conclusions also in your write-ups here. All right, and that'll be it.